Ladies and gentlemen, good morning. I welcome you to this class. I guess you are mainly from two different courses here. One part of the student population here comes from international horticulture. And if you look around, you'll see faces you've never seen before in your life, right? These are the people from the other course. And the other course is in water resources and environmental management, right? Is that correct? Okay. So you can mix. You may, okay? Talk to the others. I do have a question first to those people from water resources. Do you feel more like scientists or more like engineers? Do you know the difference between scientists and engineers? Okay. So would you rather just tell me? It's fine with me, whatever you are, right? I can deal with you. But I would simply want to know, do you rather feel as an engineer, you know, managing engineering about water resources, or you rather feel like a scientist? Any votes? Are you from water resources? No, from which course?
International horticulture.
Oh, yes, so you are a scientist anyway, right? Yes. But how about these other people with the water? Oh, who comes from water resources? You come from water resources. Are you a scientist or are you an engineer? An engineer. Okay. That's fine with me, it's wonderful. It's very important because there's a difference between science and engineering, right? In some things, and I have to know how you feel because then I can address you, hopefully at least. And then I can talk to you in a way that you say, yes, I'm an engineer and I do understand what he means. I think it's nonsense, but I do understand him, right? So I try to address also those people who are engineers because they have a different background and different expectations. Okay, so first of all, you are all here for theories and methods of research. Nobody expects anything else. If you expect something else, you are in the wrong room, right? And you should change the room. That's clear enough? Okay, now I give you some service. You get the slides here, the first page of the slides, which you can download later. I tell you everything about it, but you get it here because you may not have downloaded it. I uploaded it yesterday only, and you can download it. And today we start with something extremely thrilling, with the formalities, right? Formalities are always full of humor. They're very interesting. That's why you came here to University of Hannover, to hear something about the formalities. And I will start with the formalities first. And first, the structure of the course, which you may not know. The structure of the course is the following. We will have 11 sessions with lectures. Lectures meaning that I'm going to talk mainly, right? And I may from time to time ask you some questions, or you may interrupt me and ask me questions. That's allowed. That's fine with me, okay? We've got to talk a little. So we'll have first lectures, and that'll be approximately 11 sessions with lectures starting today till the 12th of January of 2011. That's far in the future, but as long as I survive, I will do these lectures, okay? And then we will have 3 sessions with oral presentations of research projects, okay? That will concern the MSc 13 students from international horticulture, okay? Those from international horticulture, are you from MSc 13? You are? Very good. Okay, you found the right room. You did a very good thing to come here, okay? All right, and you will give oral presentations of your research projects. You all have research projects, and the horticulture students will give oral presentations, and that's mandatory, unfortunately for you, but you will learn possibly something with it. And that'll be on the 19th, the 26th and of January and the 2nd of February in 2011. That's far in the future, so don't worry about it right now. I'm just telling you what's expecting you in the future next year, right? Okay. So, now the people from water resources don't believe you can be lazy, okay, concerning that. You have to do something as well, and you have to do the following. Now, okay, first, I'm sorry. I first tell you what the presentations are, and then I come back to the engineers and scientists from water resources. Okay, your job will be in the presentations, you have 15 minutes each. And believe me, it'll be 15 minutes and no minute more, okay? It'll be really 15 minutes because we'll have 6 people in one session and we don't have more time than 15 minutes. And in these 15 minutes, what you have to do then, you don't have to write that down, it's on the slides and you have the printout of the slides. You have in 5 minutes maximum present your project, your research project. Not everyone may know your project, and especially these people now from engineering, from water resources, they don't know anything about your project. They must know something about your project. You have got 5 minutes to present that. Then you have 5 minutes to make a connection of your project to the lectures. Now you have no idea what that means because you don't know what the content of the lectures is. But you will know after the lectures, okay, if you attend. If you don't attend and don't do anything, you don't know what the content is, right? So I may suggest that you come to the lectures, then you know what the content of the lectures is. And by the way, you may have seen the camera in the back. These lectures are recorded and you can download them later and look at them. And I just gave the permission, you can even put them down on your cell phone, right? So if you miss me, it's no problem. You simply pull out your cell phone and you look at me, right? And listen to the lectures, okay? If you don't miss me, it's fine with me as well, right? It's no problem. But you can do that. So that is not an invitation not to come to the lectures, all right? But certainly it's a possibility, but you shouldn't know that. Okay, so come back here. 5 minutes for the project, 5 minutes the connection to the lectures, whatever that will be, you will see that. I've given this course for many, many years, and that was never a problem that people understood that, what was meant there. And then finally, 5 minutes for discussion. Now, this is a very tight schedule, right? And it puts some stress on you. And that is intended, right? Why is that intended? Whatever your job will be in the future, whether back in your home country, whether you stay in Europe, whatever you do, whether you stay in science, whether you go to the administration, whether you go to politics, sooner or later, you will have to be able to give short, impressive presentations. And that must be trained. And part of what I'm going to do with you during these presentations, I tell you something about presentations, how you do present effectively. I'm trying to, of course, show you how that works, because I'm presenting here, as you may have realized already. But I'm trying to train you, and it's very important that you get a good training in that. And usually you don't get that at universities, and it's part of my mission, at least. I take that to be my mission, to train you there. So it puts some stress on you, that's right, but you have to learn that. And it's better you learn it here at the university, because if you fail, then the cost is not so high. But if you fail, then when you go home to your minister, then you say, yes, we have to do something for the environment or horticulture, whatever, then you better be effective, right? And we'll train that. But don't worry about it. I mean, I have done that many times and it never presents a problem to the students. And then we have a 5 minutes discussion after 15 minutes is finished. And the pressure is you have to keep these time limits, okay? All right, but don't worry about it. It's in the future. And as I said, it never presented any serious problems. Now to the people from water resources, as we don't have enough slots for everyone because we have just one term, the second-year students from water resources, is that right? These are the second-year students from the water resources. You are from the second year? Okay, so you know Hannover already a little? Wonderful. I don't have to introduce Hannover now? Great. Excellent. Okay, the second-year students from water resources, you have to give a written presentation of your research project. You all have research projects already, right? The older research project from the first year. Is that correct? Okay. And you have to give a written presentation, and also you have some pressure, namely the written presentation, you have maximum 1 page, where are we here? Maximum 1 page for the research project itself. I don't know your research projects, and I must understand your research projects. Therefore, you must give me information about your research project. You've got 1 page, you know, not in these letters, right? Not in a 5-point font, in a normal font. Right? Please, my eyes, you know, I want to be able to read it, okay? So, 1 page, and then also in 1 page the connection to the lectures. Again, you don't know what that means, connection to the lectures, but you will see what that means once you've seen some of the content of the lectures, okay? And here you have to hand that in by the 2nd of February 2011, 12 noon. All right, 1 minute later and I won't accept it. Probably. All right. And the way you hand it in, whether you do that via internet or email or whether in physical writing, we'll find out later. We can make compromises, okay? All right, so that's the structure of the course. So for the first 11 sessions, I will mainly talk, and you'll get some information about theories and methods of research, and then it'll be your turn. I can tell you we have had this course now for something like 12 years, I think 99. We started 11 years, and that is a format that has developed over the years. And that's a format that seems to be successful, meaning the training you are getting, because you may be quite surprised. I mean, I'm a philosopher by training and a physicist, and you may not have dreamed in your wildest dreams, right, when you came to Hannover, that you are going to be exposed to a philosopher. I mean, you are serious people, right? Serious engineers, serious scientists. You don't want to have anything to do with philosophers, right? The fact is that the experience of these earlier courses has shown that you get here something which is also called soft skills, right? Soft skills are also important, right? You learn something. And what you learn is probably, or that's at least what I hope, that you learn thinking about your science, not just doing your science and doing your engineering, but also think about it, you know, reflect upon it and make yourself become aware of certain aspects of your science, which you do not become aware of often once you simply practice it, but you think then about it. And that's the idea here, and also you get some training in the presentations. Now, let's see how that works. That doesn't tell you very much because it's so abstract, but I'll show you what I mean. Okay, that's the structure of the course. All right, any questions regarding the structure? Yes, please.
Because as you told that there are only MSc 13 second year students, but we are MSc 14 first year students. So as I see the course formalities, I could not see regarding the MSc 14 students. So
No, the MIC, they get the class next year.
but the exam in the second formality structure is, because we are MSc 14 students and it is the compulsory course for us.
Oh, you are MSc 14,
Yeah,
first year.
Yeah, we are under MSc 14 and it's the compulsory course for us. But and we could not see
Really?
Yeah.
Well, that's amazing, to say the least. That's very amazing. Because I thought, okay, I'll tell you next week. Because the idea was that now this course is given every year, and that also only the second year students are supposed to come. So are there any MSc 13 people are here as well, right? All of them? Okay, all right. And the MSc 14. And who told you that it's mandatory?
Because in our schedule it's like mandatory for MSc 14.
Okay. All right. Yeah, that may be, there is a certain mistake. Okay, I tell you next week. MSc 14. All right. How about the water resources? You are all second year students, right? Water resources, second year? All right. How many are you, by the way, water resources students? 115? 8. Okay. All right. All right. I'll find that out. I mean, I guess you should take the class next year, but perhaps something has changed and I'm not aware of it. Okay, any other questions about the structure? Anyone confused about anything? Not yet? Okay, we're working on it. All right? Okay. So, more formalities. Now, the printout of these slides you can find on the internet, right? At StudIP. Do you know the StudIP? Everyone knows StudIP. If you don't know StudIP, you cannot survive, right? You commit suicide if you don't know StudIP, right? You shouldn't do that. You're young people. You shouldn't do that, right? So if you go to StudIP, what you can find there is both the downloads of the slides in the format I've printed them out, you know. If you want to have another format for the slides to be printed out, tell me. I can also put 6 on one page, or I can put 2 on one page. I thought this is a good format because then you can write comments on the right-hand side. This is what the lines are for, all right? If you hate the lines, I'm sorry, there's no other format available in PowerPoint, so there are lines, because I heard my wife told me, she's also a professor, she told me that the students dislike the lines, but I cannot, unfortunately, I cannot erase the lines. So, but if you want to have any other format that's available to me in PowerPoint, otherwise you have to give me another version of PowerPoint, right? But if you like another version, it's no problem to upload them, right? If you want to have it 2 slides, just tell me. You know, I'm not a mind reader, not always at least. And that I don't know. You have to tell me if you want something else. And please do tell me, right? This is a suggestion. If you want to have a different format, just tell me, and then I'll try to do what I can do for you. All right, so the printout of the PowerPoint slides can be downloaded. And also I was told that in the worst case, it takes 2 days that you can also download or look at the presentation at the lectures here in video, and you can download it to your cell phone or whatever you want to do with it, okay? Right. Now, what's next? Here's a recommended book. I just tell you what you can do. It's not mandatory for you to buy this book and read it, right? The idea is, because you've got many other things to do, that in theories and methods of research, it's enough if you come here and then work with the slides, with the printout of the slides, and listen to the lectures. That's enough material, right? But if you want to do something else in addition, if you are interested in something and say, oh, that's an interesting subject, and I want to know more about it, right? Then I recommend you this book, Alan Chalmers, What is This Thing Called Science? And there's nothing about engineering in that book. If you want to know anything about philosophy of technology, that would be the area, then I will find something out for you, but I just realize it now. I have nothing in there, but yes, I will think about it as well and give you suggestions if you want to have more on that. But that's a rather accessible book, whereas other books in that area are sometimes very difficult, and for scientists and engineers, not understandable, not intelligible. But this one is a good book, and you can read it if you want. As I said, if you want. What would be the best for me is if I awake interest in you, that you say, okay, that's interesting, I want to read something about it. But as I said, it's not mandatory. If it happens, wonderful. Okay. Now, the next week I will circulate a list for the oral presentations, and then you have to write down your name and the date and the topic, but that I'll do next week, so don't worry about it, because we have to have a list. And we'll see whether it's whether you are 19 in the MSc 13 or 18 students. Probably you don't know that. I'll find out, and then I'll see whether the last 3 sessions of the course will suffice or not. Now, we'll have at the end a written examination. Okay, this is not a playground, this is a university, and therefore we'll have a written examination at the end. And that will follow the end of the term in the week just after the end of the term. That's been the practice, you probably know that. And that's the week between 7th of February and 11th of February, and probably it'll be on the 9th of February at 10:15. That's again a Wednesday at the same time, right? And probably in the same room. So it's very easy for you. You don't have to remember. You just keep going as if the term continues. You just come here. The difference being then that you get a piece of paper, right? And some questions. And you say, what's that? That's the examination. I'm telling you right now. Don't be surprised then, okay? Right? I've got it here. You've got it in front of you. That'll be the written examination. And you should also know the grading. The grading is the following. 20% of the grading will be the oral or written presentation of your research project, right? That concerns everyone, right? Everyone who wants to have this sort of certificate. And 80% will be the written examination. And for the written examination, you are not allowed to take the slides with you, okay? Because you may imagine that the written examination asks whether you have understood something on the slides, and you shouldn't be copying that during the examination from the slides. So don't be surprised if I say, please don't bring the slides with you, okay? So I tell you everything right now. Don't be surprised later. Good. Here's my email address. Email, everyone knows what email is, okay? I do have an email address, in fact, and you may contact me, right, if you want. So if you have trouble with your husband or with your wife or so, here's my email address. That's very easy. You could write to me, and then I will try to answer. But please write in English or German, right? I probably don't know your mother tongue very well, okay? All right. What else? I do have official office hours, but they are very far away. I mean, they're still in Niedersachsen, but it's very far away, right? Don't bother about it. What I will do is I make a break of something like 10 minutes during the lecture. So at 11 or so, I usually make a break, 10 minutes only. You don't smoke during the break, right? No smoking, right? For your health. I mean, you are free people, but all right, it'll be 10 minutes. And during that time, I'm approachable. I'm usually here 15 minutes or something earlier, so at about around 10, because I have to unpack the computer and everything. And then you can talk to me. So it's probably not worth it that you come to my office hours, or you can talk to me after the lecture. So I will be available. That's easier for you. But if you really want to come to my office hours, here you go. Tuesdays, in More 21, back building, 4th floor. There's an elevator, but you're not allowed to use it, right? You have to walk up. I have a key, you don't have a key, all right? But here it's flat, right? You can approach me without using any stairs. Okay, so. But if you want to come, as I said, these are my official office hours. All right, and that's it concerning the formalities, right? Anything interesting you found in the formalities, right? Really thrilling? No? Any questions about the formalities? Completely clear, complete orientation about everything. Wonderful. All right, so let's start. I start with an introduction. Okay, that's very traditional, but it's useful to start with an introduction. And the introduction is the following, that I tell you what the fundamental question of general philosophy of science is. You've waited all your life to hear this fundamental question, right, of philosophy of science. That was a joke, okay? Of course you didn't wait. You are quite surprised. Why should I care about the fundamental question of general philosophy of science? Maybe your question now. Well, you should care because that is, at least as long as you stay in class, because that is what we are dealing with here in this class. The general title is Theories and Methods of Research. And these theories and methods of research, they try to answer a certain question. And the question belongs to a certain discipline. And that discipline is called philosophy of science, right? It's just called philosophy of science. Don't worry about it. It's just a name, right? And that discipline deals with a certain question. That's the question that we deal with in this class. And that is, what is science? A very, very simple question, okay? And we are dealing with that question. We want to understand what science is, right? And theories and methods of research tell you how science proceeds in order to get the results that science wants to achieve. And I include here engineering, because engineers have a different sort of procedure than scientists usually. There are very important differences, especially when engineers interact with scientists. There are quite a lot of misunderstandings sometimes, and the engineers think about the scientists, and the scientists think about the engineers, and it's sometimes difficult because they have different thinking patterns. At any rate, although I only write here what is science, what I mean to say is that I include the engineering, and you'll see at certain points when I specifically address engineering. Okay, what is science? That's the general question. You may ask this question in different terms. Why is scientific knowledge different from other forms of knowledge? For instance, in being more reliable. I mean, why is scientific knowledge better than other knowledge? Well, most people think because scientific knowledge has some certain specific qualities. For instance, being more reliable. I mean, why are you here? Why do you spend your time? You come from countries in which probably the weather is much better than here in Niedersachsen, and it's much nicer, and you decided to come here, right? And sit here in a rainy day and listen to me. Why are you doing that? Well, I guess because you believe that scientific knowledge is something where you want to have more of it, right? You want to understand something either concerning your water resources or concerning your plants or whatever it is, what you're doing. You want to understand more about it, and you don't want to have the traditional mode of knowledge that possibly some people back home still practice. But you say, no, I want to have scientific knowledge, right? I don't want to have everyday knowledge. I don't want to have voodoo knowledge. I want to have scientific knowledge. And why do you want to have scientific knowledge? Well, you probably don't really know, right? But I guess you have the hope that scientific knowledge is somehow better, somehow specific. It's something else, right? Something you want to rely on, right? Most of you probably have some sort of cultural tension, right? Because this scientific knowledge is knowledge generated and mostly practiced in the Western countries, right? In the industrial world. And some of you come from countries that are less industrialized, and scientific knowledge is less pervasive in these countries. And you decided you took a very brave decision. You said, I want to have more scientific knowledge. I have to go in order to get the best education. I have to go to a different country. You choose Germany, you choose Niedersachsen, you choose Hanover, and now you're sitting here. So you are living proof that you believe in a specific quality of scientific knowledge. Otherwise, you wouldn't be here, right? But the question is, and that's the question of this class, I mean, what is it? What is specific about this scientific knowledge? Why is it different? In which sense is it different? Right? Can we understand why scientific knowledge is different and better than other forms of knowledge? Right? That's the question we are addressing here. Okay? So it is something that does concern you, right? Even if you can't use it immediately in your research project. You will find out you can't immediately do it, but the experience tells us from this class from the last 10 years that it is useful to you, that you start thinking about science and you learn something. Okay, that's a program and promise, don't believe promises, but you'll find out yourself. Okay, so that's the question, why is scientific knowledge different from other forms of knowledge, for instance, in being more reliable or whatever, or more systematic or whatever it is. All right? Or in other words, what are the characteristic features of scientific knowledge? Or what is the specificity of scientific knowledge? Why, in what sense exactly is it different from other forms of knowledge? Right. Now, what I'm going to do, how I tackle this question, is not that I simply tell you all the truth about science, right? The reason is there is, with the relevant people here, philosophers of science or scientists themselves, there is not really a wide consensus exactly about what science is, right? That's different, say, if you look at evolutionary theory or if you look at hydrodynamics. If you look at hydrodynamics, there is a consensus about everyone, about the fundamental principles of hydrodynamics, right? You have flow equations or whatever, and you have conservation laws and whatnot. Or if you look at biology, I mean, there are a few very strange people, but I mean, everyone really being a specialist in biology accepts evolutionary theory nowadays. Yeah? There are some people who don't, but they're rather strange somehow. At any rate, so there is a consensus. If you look at many areas of engineering or many areas of science, there's a characteristic feature that there is a consensus, that people come to agree how that works or what the basic principles are. And that is different in that area in which we are moving, philosophy of science, and there is not really a consensus. There are different answers. And what one has to learn if one thinks about science is to cope with this variety of answers, because you don't get simply one answer and you can take it home and say, I know the truth about science. That's unfortunately not so easy. It's such a tricky and difficult subject that people don't reach an easy consensus, but still one can talk sensibly about it, and that is what I'm going to do. And what I'm going to do is I will present you 4 specific answers to these questions, what science is and what specific is about science, to these questions, and which have been given during the last 100 years. So what you'll hear then is a panorama, so to speak, a spectrum of answers, and we're going to discuss these answers, what their strengths, what their weaknesses are, and that is the sort of training you should get here, namely thinking about science and thinking about arguments, and then trying to understand the different positions, and then finding arguments why this position is better than that position, and so on. So it's a sort of training to think about science. That is what you're getting. And I'm doing that in presenting you 4 specific answers to these questions. And now I present you simply the titles of these answers. I don't expect that you understand these titles. Inductivism. Have you ever heard the word inductivism in your life? Who has heard the word inductivism? Have you heard about the problem of induction or something? No. Very good. So it'll be full of surprises what you'll hear here, right? Many new things, and you say, wow, isn't that interesting, or isn't that boring, whatever. Inductivism, deductivism, paradigm theory, and systematicity theory. So you don't know anything what that means. These are just the titles, the names of certain positions, and I'm going to explain to you these positions, all right? And what I'm going to do, I'm telling you right now, because you will be surprised in the course of that class, I will first present these answers as persuasively as possible. So what I want to do is, when I talk about in this position inductivism, what I want to achieve is that once I finished my presentation of that position, that you say, wow, now I know what science is, right? That's the right answer. And then you say, wow, yes, I'm an inductivist. Boo, I tell my mother, write her an email, right? I'm an inductivist now, ma'am. It's wonderful, I know what science is, right? That is what I try to do. And then I will try to criticize, right, that position, that inductivist position, and show you that, well, you first be completely convinced, and you see, wow, there are critical remarks. Oh, damn it. Oh, that's difficult. Oh, it doesn't really work, right? And then you are very disappointed, right? And again, write again to your mother or your sister and say, I'm very disappointed, Mom, inductivism doesn't work, okay? And then I'll do the same again. Then I present you deductivism, because deductivism will be an answer to the problems of inductivism, right? Deductivism is a different position. Again, you don't know what that means. It's a different position that was developed because of the problems of inductivism. And deductivism said, I can heal, all these problems here. I can, I have a good medicine against it. And I tell you really what science is, right? And I'm going to tell you what the answer of deductivism is, such that at the end of the presentation of deductivism says, my God, I'm so happy that I'm not an inductivist anymore, because now I'm a deductivist, and now I know the truth about science, right? Yes, but then I'll start the same game again, and I'll show you what the problems of deductivism are. And then you get counter-arguments against deductivism. And that I do 4 times, right? So the training you're getting is that you start thinking, and I'm trying to really seduce you into inductivism. I'm going to seduce you into deductivism by presenting it in the strongest possible form I know of, and make it as plausible and seductive and convincing as possible. And then I will criticize it afterwards. And that's the idea, of playing this sort of dialectic, as one says in English, that dialectic, of arguments, counter-arguments, and pro-arguments and counter-arguments. And that is why we do this class. You learn these positions, right, that if you find sooner or later in the literature or in discussions, you find these positions, then you know what these positions mean, and also you know arguments about these positions, why they could be good, or what the weaknesses are, and so on and so forth, right? So I summarized that after an attempt to present these answers as persuasively as possible, criticism of them is raised, which forces the development of new answers, right? And that's the idea. So this is really different from science, right? That is not a procedure you have experienced in your life in science, because in science the usual thing is that you learn a new theory or a set of devices or a new model or whatever it is, and the mode of presentation is, of course, that you learn it, and the idea is then you can use it, right? And that is because in the sciences you have, at least often, not always, but often, you do have a consensus, and it is quite clear that you can use the theory. It makes sense to use the theory or model or whatever it is, or procedure, measurement procedure, whatever it is, or optimization procedure, whatever it is. And therefore, there is no need for that sort of procedure to discuss something. But as we are in this field where we do not have a consensus about what science is, on the other hand, we are interested in that, and it's useful for you to have this sort of discussion. I use this mode of presentation, okay? Again, this is still a little abstract, but I'm just telling you, don't be too disappointed when I first behave as if I was really an inductivist, and I tell you every truth about science by telling you inductivism, and then two hours later, a week later, I say, inductivism doesn't work. No way. Okay, so I've not changed in the meantime. It's not that I'm schizophrenic or something. It's just normal, right? So I'm just telling you, it's somewhat different than the other classes you're attending. All right. So we start with inductivism. Any questions concerning that procedure? Is it at least a little plausible why that could be done that way? I mean, it's very abstract. You cannot really imagine what's going on. Is that plausible? Any questions about that? Okay. Then let's start with inductivism. And you will see that I'll start all these lectures that I first give you the basic idea, right? So to speak, in one sentence that you understand what that position, what the main aim or the main thrust of such a position is. The main idea, and that idea will then be a little bit developed and such that it becomes more extended, and then we'll see. We go to the criticism. So the basic idea of inductivism, we have to start with something, with an observation which is rather simple, but I have to make it explicit here because otherwise we don't understand the procedure of inductivism and the main idea of inductivism. It's the observation that in science and engineering we find singular statements and general statements, right? Singular statements, never heard that possibly. I'm going to explain to you. What are singular statements? Singular statements, for instance, now I try to use examples from your area, right? I told you already, my original training is in physics, so I'm not a water engineer. I have no idea. Well, I read a little, but I don't know very much about it. I know a little more about horticulture science because I heard so many presentations by the horticulture students during the last 10 years, so I learned a little about it. So if my examples are really stupid, then please tell me. If the water people tell me, look, this is nonsense. Well, I looked it up in the internet. There are lakes that are contaminated by pesticides and heavy metals, right? Am I not right? There are lakes. They are heavily contaminated. So now imagine you stand in front of such a lake, and then a water engineer says, this lake is contaminated by pesticides and heavy metals. That's a singular statement. A singular statement because you speak about a singular object in front of you, right? That lake, and you say something about that lake, okay? Now the horticulture people will say, I don't understand this example, right? Because I'm not a water engineer. Am I not right? Not really? Okay, I have now this is the example for the horticulture students, right? This plant has 9 leaves. Yeah, you imagine you have the plant in front of you, you count the leaves, and then you say, this plant has 9 leaves. I know it's sometimes important to count the leaves, right? Not for all of you, those who do economics of horticulture, of course, don't care about leaves at all. They see money, right? For instance, export, import, gross national product, whatever. Okay, but you can't, I think everyone can understand this one. This plant has 9 leaves. That's a singular statement. Why? Not because the number 9 is here, because you talk about that plant in front of you, right? About this singular little thing, that plant, or big thing, maybe a big, well, if big things have usually more than 9 leaves, but imagine winter time, right? Then the big oak may have 9 leaves. We'll come to that state. I'll give you examples then when you look out, okay? Here are examples both for the engineers and for the horticulture students. All right, back here, please. Concentrate here on that. This plant has 9 leaves. That's a singular statement. Now, true singular statements express singular facts. If a singular statement is true, then it expresses something, and expresses a singular fact, namely, for instance, this one expresses the fact that the lake is contaminated by pesticides and heavy metals, right? And the other one expresses the fact that the plant has 9 leaves. That's very simple, but it's important to be aware that you say, okay, what's a singular statement? Oh, if a singular statement is true, then it expresses a singular fact, right? A fact like this plant has 9 leaves. Okay. Sounds very trivial. Now, in science and engineering, the singular statements that you find there often, not always, but often express observable and or measurable facts. So if you do an analysis of a certain lake, for instance, and you are asked as a water engineer, you say, look, this lake, it's very funny that the fish are all dead in this lake. Isn't that an accident, or what happened? And then you say, well, haha, very simple. We just look at the contamination of that lake, right? And you measure the pesticides, and you measure the heavy metals in there, and you find 50% is not water but heavy metals, for instance, which is a very high concentration, I know, and I'm exaggerating a little, okay? Then you say, okay, I have established the fact that this lake is contaminated by heavy metals, and you can express that singular fact, and you establish that fact by measuring them or by observing them. So for the horticulture scientists, you establish that fact, that 9 leaves, that you observe it and you count it, and you say, yes, here, that's the fact, right? So many of these singular statements that you find in these areas, both in science and in engineering, they are singular statements that express observable facts. Not all facts are observable, right? If you go to cosmology, right, that's not a field that you study here. In cosmology, where you study the history of the cosmos, then today's cosmologists, they state the fact there was a big bang in the beginning of everything, right? That's a fact about that's a singular statement about a singular fact. Well, if it is a fact, I mean, people believe it, okay? And that's, of course, not observable. You cannot ask a cosmologist, oh, let's go out and let's observe the Big Bang, right? That's not possible. Why not? Well, it was in the past, for instance. And if you could observe it, you wouldn't survive it, right? And you didn't, well, it's quite clear. Does everyone know what the Big Bang is? It's a rather big bang, right? It's very loud. Is it loud? No, it's not loud because you have no air, right? Okay. All right. In science and engineering, often expressed, therefore I say often here, observable facts, and that will be the starting point of the position. I'm not telling you because I want to impress you what I know about singular facts, because that's the basic then of inductivism, because that'll be the starting point of inductivism, namely the singular statements that express observable facts. That is where I move to, okay? And therefore I have here this distinction between the singular statements and the general statements. So that is the case, and we will see that that will be the starting point of that position that I'm going to develop that is called inductivism. And you still don't know why this is called inductivism, which is fine. All right? So these are the singular facts. Now, in this case, if a singular statement expresses an observable fact, then it's easy to verify the statement. To verify means to find out the truth of the statement. Right? It's very easy. Because what you do, you observe or measure and you will know, right? So if someone tells you, look, this lake is very contaminated, or if someone says the river Leine is very contaminated by this and that, by pesticides, you say, well, I don't know, perhaps he's right, perhaps he's wrong. And if someone says, well, please establish the fact whether the Leine is contaminated by pesticides and heavy metals, you say, very easy. You pull out your measuring instruments, go to the line and measure it, and then you establish it. Said, well, the concentration of this and that and that is so high and high. Yes, that counts as contaminated. Therefore, the line is contaminated. So it's no big deal, really, to find out whether a singular statement is true or not. In many cases, if it is a singular statement about observable facts or measurable facts. But what you do is very simple. You go there and observe it, or you go there and measure it, and then you know, right? So if someone claims this tree here has, you don't see that if I point out there. This tree here has 1,400 leaves, right? In principle, you simply go out, spend your lunch there, don't eat, don't drink, and count the leaves, right? And then you say, no, it's not 1,400, it's something else, 1,200 or whatever, right? But in principle, you know exactly what to do if you want to find out whether a certain observable statement is true or not. You simply go there and you measure and observe. And that's very simple with singular facts. It's very simple because in singular facts you have one object you have to look at, right? One, the lake in front of you, or the river Leine, or that particular tree, or a particular plant. You look at it and observe it and measure it, and then you know, right? And that's comparatively simple, right? But science isn't that simple because it does not only contain singular statements, it also contains something else. namely different general statements in the sciences. And the question why I made this distinction here between singular statements and general statements is that the procedure to find out whether statements are true, these procedures are different for singular statements and for general statements, right? And as we are interested in science, whether it's true and whether it's good knowledge and so on and so forth, we are interested in how do the sciences find out whether something is true or not. And because the procedures are different for singular statements and general statements, I made the difference between these sorts of statements, right? And the point is that the problem with finding out whether a scientific statement is true or not, or an engineering science statement is true or not, the problem does not really arise with the singular statements because they are fairly often quite unproblematic. You simply measure or simply observe, right, the singular case. But the problem is when you come to the general statements, right? And the general statements present problems, and these problems then provoke this position which is called inductivism. And therefore I make this distinction, just that you know what I'm doing here and why I'm doing it, okay? So, in earlier classes people asked me I should say more about these terms that are going to come now, the terms like hypothesis, theory, model and so on, because you use these terms but you don't really know what they mean very often. At least people told me, students told me. Therefore I did that for the first time. This is now a premiere, right? You are the first one who sees that. Nobody else has seen that before. Isn't that wonderful? Well, let's see whether it's good. Then we'll find out. There are different kinds of general statements in the sciences, and I want to talk about this difference of the general statements. Now, let's see whether, yes. There are things like natural laws. All of you heard of natural laws, of course, because you have studied natural science and engineering. Natural laws like Newton's law of gravitation. That's a general statement. It tells you something about all cases of gravitation, right? That's the idea of a natural law. It tells you something very solid. And if you want to remember, that means the force is gamma, that's the gravitational constant, then mass 1 times mass 2 divided by the square of the distance. It tells you that's Newton's law of gravitation, as you have all in the slides, right? If you copy that, you copy it, it's on the slide, it's in the printout, okay? Have you seen it? Have you got the printout? Right, it's there, yeah? Oh, I'm sorry, is that already, that's the number 7, okay. Yes, you can download it, okay? I'm sorry, I didn't realize we are already at number 7. I only gave you 6, you know, in order to force you to go to StudIP. No, you can download it there, right? Okay. So, but yeah, so you may take notes now, but I promise it's there. We checked it just before. It's there on StudIP. You can download it unless the mainframe breaks down. Okay. Now, okay. So this is Newton's law. Who has never heard of Newton's law of gravitation? Very good. You are too shy to show me who haven't heard. Anyway. Now, the point is with natural laws, when in science something is called a natural law, like Newton's law of gravitation, it's, first of all, of course, it's a general statement. You don't say anything about something very specific. You don't talk about the Earth or the Sun, or for instance, this little instrument has also gravitation, and it gravitationally interacts with the Earth. If I let loose now, then we'll see the gravitational interaction very clearly. They are supposed to be certain. When scientists, natural scientists, speak about laws, natural laws, they think they really know the laws, and the law is certain, and it's usually, or very often, there are exceptionalist laws, and you simply know that they are true, right? They are supposed to be certain. Natural laws are general statements that are certain, okay? Then we have something else. Natural scientists don't only speak about natural laws, they also speak about theories. In other words, theory means different things in different contexts. It's not that it's always the same thing, what you mean when you say theory. And what does that mean? Well, it may mean very well established, very general statements, like, say, Darwin's theory of evolution or quantum theory. I mean, here you even see theory, Darwin's theory of evolution, right? So this is something extremely general. Darwin's theory of evolution is supposed to apply to everything living on Earth, right? Just everything. everything was evolved according to mutation and selection, to put it in a very short form, Darwin's theory of evolution, or quantum theory, if you look at things that are rather small, with low energy, then with little energies, say atoms, or molecules, or something, then quantum theory applies. And the idea is that quantum theory applies really absolutely exceptionlessly, right? All the cases of molecules, atoms or so, obey the laws of quantum theory, right? That's the idea. The same with Darwin theories. So we speak about theories in the natural sciences, very well established and very general statements, right? Very general meaning here in Darwin's theory of evolution. Just every organism is supposed to have evolved according to Darwin's theory. Or in quantum theory, just every sort of atom, every sort of nucleus, every sort of molecule obeys the laws of quantum mechanics. That's the idea of theory, and very well established. So if you today say a biologist, and you say, well, I don't think that Darwin's theory is right, I think that's nonsense. I mean, better go home, right? I mean, all the other biologists will say, sorry, wrong class. Okay. It's so well established, the same if you are a physicist and say, no, quantum theory is false. I mean, it's very simple. Then people will say, you're crazy, right? You don't understand what you're talking about. So these are very well established, and you have, of course, this is one sort of meaning, or one way how to use the term theory for these very well established, very general statements, like Darwin's theory of evolution. There are other theories, of course, but these are just two examples. That's one way of using the word theory. But there is another use of theory, and that means really something different, but we also call it theory, and that's general statements about which you are unsure. So it's just the opposite. Here you are unsure, and here it's very well established. When you say it's just a theory, right? If someone says, you know, blah, blah, and then someone answers, well, you know, this is just a theory, meaning, well, you can't be too sure about it. You know, this is what you think. And that's also what is called a hypothesis. You know, when people say that's a hypothesis, then, you know, you are unsure. You play around with it and you say, yes, it's a hypothesis. I look at it, I consider it, I may analyze it, I may do some research on the basis of that hypothesis. But by saying it's a hypothesis, I'm expressing that I'm not sure of it. It's not certain that it is true, right? And that is also a use of theory. It's just a theory or hypothesis. By this term, you express your possible doubt about it. You're not saying it's false, but you say, look, I don't really know whether it's true or not. And that is why we use in science then the term hypothesis, because we very often deal with general statements about something, and we are not yet sure whether it's right. So I guess, I mean, isn't it in horticulture science, you have to formulate, when you do your outline of your research project, you have to hypothesis, you know, and that's the idea, the hypothesis is, and then you go to the next section is then, what is it, testing or methodological procedure, methods or what? How to test the hypothesis, right? And if you admit that you have to test the hypothesis, of course you admit that you are not completely sure that's true, but the point is that you say, well, that's interesting, right? If for instance, sunlight now influences the growth of these plants in such and such a way, say, yeah, that's my hypothesis, let's test it, right? And then you play around with the sun and play, well, that's a little difficult, but you may play around with artificial light, right? And then look what the impact of the light is, and so on and so forth. So that's an hypothesis, something you play around with. You may show that it's true, or you may even you may want to show in other contexts that it's false. But the point is that you are not sure about it, right? That's the idea of hypothesis. And sometimes you use the term theory in the same way, but be careful. It's really very different when you use it. It's just a theory. You don't mean something as solid as quantum mechanics, right? Certainly not. But you want to say, look, I'm not really sure whether it's true, and I want to consider it, I want to test it, or I want to confirm it, or justify it, or whatever. All right. So this is the term theories. But there are here, for instance, this is a wonderful example for the horticulture people. My theory or my hypothesis is that plants of species X are not seriously affected by a change in their environmental condition. Why? Right? That is something where the horticulture students find themselves. Say, yes, that sounds familiar. Yes? Wonderful. Not for the economists, right, among you. Perhaps I have an example later for the economists as well, all right? There are so many different people here, so I can't do everything for everyone at the same time. Right, so you have my theory is that, and that means then, yes, you know something about these plants of species X, and you say, well, I guess this is the case, they are not seriously affected by a change in environmental condition Y, and then your supervisor tells you, so, devise an experiment, tell me what the methods are to test this hypothesis. And then you say, okay, I put 400 plants there, and then I systematically change environmental condition Y, and then I look, and then I count the plants, what is the effect, and blah, 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 all right? So this is the dealing with hypotheses because you don't know whether they are true, and what you want to do is you want to establish, well, their truth or falsity is a little high, but at least you want to have arguments to defend the hypothesis, or you want to have argument to attack the hypothesis, right? You want to deal with it, whether it's more true or less true or not true, or something like that. You want to evaluate it according to its, one could say, truth content, whatever that is. Okay, so this is theories and hypotheses. These are terms that are used in science, and we are now a little clearer about what they may mean. I continue 5 more minutes, and then we have a short break. Okay? And then we have something which you may hear probably in engineering as well, and in the sciences, that one speaks about regularities or empirical regularities. You also find that, of course, in the social sciences. Are any social scientists here as well? People with a social science training? No. Okay, so you learn something about the social sciences as well. Oh, we have a social scientist in the back, but that doesn't count today. All right, empirical regularities. And these are, in principle, these are general regular relations. It's a general, well, here it's a plural and here's a singular, I'm sorry. A general regular relation between different variables, right? You have a connection between variables, and that's regular. So if you change variable A a little, and then variable B changes in a certain way, and the connection between the two is expressed by the regularity, right? Is that a way engineers speak as well about regularities? Engineers sometimes, if you have a table and you have, say, variables on one side and the dependent variables on the other side, you call that a table probably, just a table, function or whatever. Yeah, function. Okay, empirical regularities. That's a term that's also used in the sciences in different branches. And finally, there is something which is called a model. That a model is also a general thing. It applies to many different cases usually, and the model is also such a general statement, and here it is typically a simplified image of a general relation among different variables, right? So, I come to an example later. For instance, one speaks about model organisms. Any idea? Can someone give me an example of a model organism in biology? Right, it's a plant, right? And there are, of course, animals as well, where you have that's the specific plant, this model, or you have other models. These are, I mean, they are simpler than other plants. That's the belief, at least. So if you want to experiment on plants and you have complicated plants, then you say, okay, let's first experiment with these model organisms because they exhibit then in a simpler way what we want to understand, right? And that is model organisms. The idea is, this is of course not an image of a general relation, but a sort of image. It's in model organisms that you can investigate something, and you hope then that in the model organism it's simpler than in other cases, but you have a hope, of course, that you can transfer that something you learn about the model organism can be transferred to other organisms. That's a hope that's sometimes justified, sometimes not. That's not my point. My point is here simply that you become aware what the term model means. It's another thing is when you speak of a model of an economy is a very, very, very complicated. Are economists here as well, hopefully, from the horticulture science? Yes, good. Economists. So when you speak a model of an economy, you say, okay, I mean, there may be 1 million households and 10,000 firms, and 15,000 governmental agencies that all interact, and it's a mess and complicated, and you can't say anything about it. So you say, let's make a simplified model, right? We make a model of a million households, and they have all the same preferences, for instance. And we model the governmental agencies. We model they have laws, and they restrict the actions of the households, and so on and so forth. You simplify, right? You make a simplified image of the general relations. Or if you take the model of a lake, for instance, if you have a certain lake, and this is now for the water people, if you have a lake, I mean, the lake is very complicated, it has a very complicated topography, and you want to understand what happens with the lake, and you have outflows and inflows and evaporation, and you have minerals, and you have whatnot and damages, and so on and so forth. And you can't. If you look at that lake, you can't really have all the details. So what you say, let's make a model of the lake. Let's assume the model is just round, right? It's not. Of course, in reality, it's not round. Let's make it round, and it's got constant depth, right? 15 meters, period. And then I've got the volume of the water that I want to investigate. And we assume it's just water in, and we have one inflow, one outflow, and evaporation rate such and such. You simplify, and what you do really is you have general relations, and then you say, yes, the general relations are then with the inflow and the outflow in this model is such and such. And then you model the lake, and you have general, that is the very important point here, general relations. So, as I said, we have in the sciences and in engineering, we have very different sorts of things which are general statements. The general statements may express theories, they may express empirical regularities, they may express models. Yes. Now the important point is why I made the difference, I told you earlier, between the singular statements and the general statements is this, that the general statements, that means laws, theories, general hypotheses, regularities, and models, they cannot be verified in the same way as singular statements. And why not? Because they refer to indefinitely many facts. It's not just one fact, but very many. I give you an example, okay? Now, I first tell you that this is problematic. The so-called generalization of singular statements to general statements is problematic. You are not talking about a singular case where you can make a decision what is the case by looking at it and measuring it, because you talk about many, many cases. And just look at the following case. That's a standard example. For example, consider the generalization from the observation of some finite number of swans that are white. If you observe this, so you go to the, I don't know where the swans are in Hannover, in the zoo, for instance, or perhaps on the Leine, and you go there and you observe the swans, and all the swans are white, and then you say, well, I've seen now 15 of them, all swans are white. Okay? Is that a good generalization that all swans are white? No? Who comes from Australia? Nobody, but you've read it. There are black swans, right? It happens to be the case. There are just black swans. So the generalization from your observations that you do here in Europe, unless you go to the zoo where they have black swans, but if you just go to the rivers and to the lakes, say in Germany, and watch the swans, and then you say, yes, I've seen them, and now I give you a general hypothesis about swans, namely all swans are white. This is tricky because you haven't seen all swans, but you talk about all swans, right? And that's the problem with the general statements, because you talk about all sorts of things with the general statements, but you haven't seen all of them, right? And that's the problem, right? But what happens is in science that we want to have the general statements. I tell you after the break why we want to have the general statements. We need them, right? It's not enough in science just to say, okay, that's too dangerous. Let's forget about general statements. Only talk about this plant and that plant. I give it names. This is Anna, this is Franz, and this is Jim. That's not enough, right? Your supervisor would be very unhappy with you if you say, no, I refuse to talk about general things. I only talk about this particular plant. Say, no, sorry. In science, we have to have general knowledge about plants, about a certain species, for instance, because we want to not export this particular little plant that is dead in 3 years from now, but we want to have this species of plant and want to look what it does in that environment, all sorts of them, all singular specimens of that species. So we are interested in general knowledge. I'll tell you more about that later. So we have to have general statements, but we have a problem with the general statements. You know, it's difficult to find out whether they are good statements, whether they are right, whether they are true, right? Because there are so many cases. And you see here, when you simply say, well, look at the number of swans and you find out their color, yes, but you can make a mistake here, a grave mistake, that you say all swans are white, and it's just not true, because there are black swans. You unfortunately haven't seen any one of them. Okay, so there we now approach that problem. And okay, that's good enough for now. So we make a short break now of, say, 8 to 10 minutes. And then you please come back, and then I continue.